So now next question is, a particle moves along an orbit r equals to a cos psi under the influence of a central field given by fr. Then you are required to find the r dependence of the force. So whenever you are required to find the r dependence of the force, then you need to use the orbital differential equation. Orbital differential equation. We also commonly refer it to as Binet's equation. So Binet equation is of form f as a function of u minus m h square u square, then double derivative of u with respect to theta square plus u. So now the question is, what is u? So u is nothing but it is inverse of r. Okay, so u is 1 by r, and we know that r is a cos psi. So in that way, we define u is nothing but a prime sec psi, where a prime is the inverse of a. Now we are required to find the double derivative to plug the relation in this space. So we are required to calculate single derivative of u with respect to psi and then double derivative of u with respect to psi. We are not going to spend much time in differentiation because we all know it. So the double differentiation of u with respect to psi will be a prime sec psi within bracket tan square psi plus sec square psi. Then we are going to insert it here, this relation here, and we already know the u is nothing but a prime sec psi. So whenever we plug this all, and we know that h is nothing but r square theta derivative, u we know, and this is for the unit mass because there is no mass term here. So to simplify it, we are using the unit mass case, and h is, as I said, it is angular momentum per unit mass, and it is a constant in this case. Now we will substitute all the values in the expression, and then we will simplify. We will require some trigonometric identities such as tan square psi plus sec square psi to solve and get 2 sec square psi minus 1. When we substitute all the values, we get 2h square a prime cube multiplied by sec to the power 5 psi. And then when we substitute back all the original terms, we finally get f as a function of r is equal to 2h square divided by a square multiplied by 1 plus r to the power 5. So the central force that results in orbit given by r equals to a cos psi is given by this, and it is fifth power of the radial distance in inverse, and it is negative, which also tells that it is attractive in nature. Now let us move to the 16th question. A particle moves in a circular orbit under the action of force given by F as a function of r equals to minus k r square. If k is suddenly reduced to half its original value, so that the particle would move along a parabola. So originally, the particle was moving in circular orbit using the force given by minus k by r square. But now there is some change, and the force become minus k by 2. It is going to half, and it is r square. Okay. So let us try to understand the general equation of orbit. So for any motion under the central force of form given by minus k divided by r square, the eccentricity E of the orbit is directly related to the particle's total energy per unit mass. Okay, this is the important formula which you must memorize at any cost. Okay, important formula because it relates energy to eccentricity of the orbit. Now, the total energy per unit mass will be the sum of its kinetic and potential energies, and you can find the potential energy using the formula. As the force is conservative, so we can always write it as a gradient of any scalar function v. So in that case, if you try to find v with some integration, you will find that it is going to be k by r, and kinetic energy will be half mv square. Kinetic energy will be half mv square. For unit mass, it is going to be half v square. So this is what we have written in this particular expression. Now let me tell you, if you recall from your classes or not, the shape of orbit is determined by the value of E and thus eccentricity, because eccentricity depends on the value of energy. So if energy is less than 0, then we can say that eccentricity is going to be 0 or it is going to be less than 1. Okay, so this orbit is bound and it is either ellipse or the circle. Circle when eccentricity is going to be 0. Okay. Now, when energy is 0, so it leads to a straightforward result that eccentricity is 1, and this is unique case of parabola. This is what we need to prove. So, you might have guessed right that either we need to prove that energy is 0 or we are required to prove that eccentricity is 1. Now, when energy is greater than 0, so eccentricity is obviously going to be greater than 1, and this orbit is hyperbola. And let me tell you, this has been as a PYQ. Okay. So step 2, we are analyzing the initial circular orbit. So let the radius of the initial circular orbit be r0, and for the orbit to be circular, the attractive force must exactly provide the required centripetal force to keep the particle moving in a circle. In that case, we can write that centripetal force is going to be equal to attractive force. Okay. In that case, centripetal force is mb square by r equal and it is equal to gmm by r square. So in general, this is what we have written here, and as there is no unit mass, there is mass of unity, that is mass is only we are considering 1 kilogram. So this is going to be v naught square divided by r naught is equals to k divided by r naught square, and we will use it later. Now try to write the initial energy, because we are going to find the energy, and if you find energy, we will get the value of eccentricity. So it is very important to find the value of energy. But to find the value of energy, we are required to find the value of kinetic energy. So kinetic energy of the particle per unit mass in the circular orbit will be given by half m v naught square, and m is 1, so it is going to be half v naught square, and v naught square we can get it from this expression. Okay, this expression will provide the v naught square, and v naught square is nothing but you can sense that it is going to be k by r naught. Okay, so when you put the k by r naught, we are going to get half k by r naught or k by 2 r naught. Now we can calculate the total energy per unit mass, and we are calling it E initial for the circular orbit, and we already have the value of potential energy, and we are going to substitute the value of kinetic energy, and finally it is going to add up to provide us minus k divided by 2 r naught, and minus sign here also confirms that it is bound orbit and it is circular orbit. Okay. And if you want to test that, you test this value in the eccentricity example. E square equals to 1 plus 2e h square divided by k square. So if you put the value of energy here, you will get it to be 0. Okay, so in that way you can ascertain that it is circular orbit and as it was expected initially. But there is sudden change. In the force constant. Okay, and force constant was initially k, but some changes happen and it becomes a by 2. Okay. So the problem states that the force constant k is suddenly reduced to half its value, and this is crucial detail. Suddenly means the change happens over an infinitesimally small time or short time interval. In this instant or at this instant, the particle does not have time to move or change its velocity. Therefore, at the moment of the change, okay, the particle position would be still same, the particle's velocity would be still same, but the force constant would change to k by 2. and the particle now finds itself with its old velocity at its old position, but under the influence of new weaker force because it has been halved. Now let us try to find or calculate the new total energy. So we must now calculate the particle's new total energy E nu under these new circumstances. The kinetic energy is unchanged because there is unchanged at that particular moment because there is no change in velocity as we described above. But now the potential energy will definitely change because potential energy depends on the force and the K has changed, so force has changed, so potential energy will change as well. So let us try to formulate the new energy, that is kinetic energy plus sum of new potential energy, and new potential energy will be K prime divided by R naught. So we could write it K by 2 divided by R naught, and finally when we do it we get energy to be 0. And if energy is 0, then we know that E square leaves us with 1 and E is simply 1, and this is nothing but parabola. This is nothing but parabola. Okay. This equation we have used again and we got E nu to be parabola. So let us write the conclusion that when the force constant K suddenly halved, the particle's total energy changes from the negative value and corresponding to a bound circular orbit to exactly 0, which is parabolic orbit. An orbit with total 0 energy has an eccentricity of 1. By definition, an orbit with eccentricity 1 is nothing but parabola. Therefore, obviously, the particle is going to depart from its circular path and move along a new parabolic trajectory.